is that you have all this map, you have a map, and you have representations. You choose a basis, and you have to go through this regular row to find the matrix when the bases aren't the standard bases, right? Or asking what's the representation of a vector in different bases, and that sort of seems like this extra thing that's going on. It has something to do with bases. Now, the next chapter has a section, not the first section, but let's look at the table of contents and see. So if I look at, see the maps and matrices chapter, you have the action of linear maps, matrices for map combinations, which is sort of what you've sort of reviewed a little bit here. But then there's two chapters. Let me see, there's a chapter on the geometry of projection maps, and then there's something about bases. So these chapters should probably be reversed in order. This is about the geometry in vector spaces. So we're going to do that, but right now, I think the thing is here, we've got stuff on bases. Now, the second one here is using the geometry to find bases that in some sense are perpendicular to each other, to show that if we have a geometry, we can say that vectors, we can bring in the fact that there's an angle between vectors, and so we can find bases where the basis vectors are not only linearly independent, but they're also orthogonal, perpendicular to each other, and that's useful. That's like your XYZ axes. You chose them perpendicular usually for a reason, so they're sort of like don't interfere with each other. But here's this section here of chapter 9 on bases, which is what I would like to look at now. So we're sort of jumping a little bit to chapter 9, section 1, then back to chapter 8. Okay? So it's like a way that I'll sometime in the future reorganize the text a little bit to be a little bit less okay. So now this section isn't that bad, because section 9, chapter 9, section 1 deals with matrix representations of the identity map. Okay, so the map here, I, from V to V, always takes V to itself. Okay? Well, that seems really simple, right? Or trivial, right? Because let's say that I had a basis B here that was just some V1 and V2, right? And let's say that I also had the same basis B of V1 and V2 for V. So I use the same basis for V each time. So what is the identity map? Well, the identity map just takes every vector to itself, right? So the question is then, well, what's the representation of the identity map? The matrix representation, right? Well, let's just go through and do what's the basis action? Like we want to find the basis action of the identity map. Well, the identity map takes V1 to V1, right? So that equals 1 times V1 plus 0 times V2. So as a matrix, it's 1, 0 in basis B. Well, I want to find the image of the second basis vector, V2. Well, it's identity map, so it goes to V2, but that's equal to 0 times V1 plus 1 times V2. And that equals 0, the vector, the column vector, because the representation is always column vector 0, 1 in basis B. So I, from basis B to basis B, equals 1, 0, 0, 1. So this identity map, this form of the identity map always takes vectors in a space in the identity map always goes from a vector space to the same vector space because they're identity maps. Okay, but they all, and so if you don't change basis, this identity map representation is just saying, okay, the first basis vector goes to the first basis vector, the second basis vector goes to the second basis vector, right? So the vector AB is going to go to the vector AB. In other words, if I write any vector V has some decomposition A V1 plus B V2, which equals AB in basis B. So if I take A, this I, like here, and that's going to give me 1, 0, 0, 1 AB, which equals AB. It didn't matter. It doesn't matter what V1 is. If it's a so although this may seem trivial or obvious or something like sleight of hand, the point is these don't have to be standard basis vectors. If the identity map from one basis to the same basis is always this identity map here. But something else is going to happen if we change the basis vectors, right? So let's look at the same thing. Let's look at the identity map from V to V, but let's choose B equals V1, V2 here, and choose D equals to V1 plus V2 and V1 minus V2 as our basis, as a second basis, right? So what's the identity map that takes a vector? It still takes a vector to itself, right, as a map. But if I look at the representation, it's going to map a vector in basis B to the same vector in basis D. So the identity map acting between different bases is a change of basis representation. It's the thing that's doing what I've told you to do by hand is, okay, we have this vector in basis B. What is its representation of basis D? This can be implemented by it's an identity map. It's saying what's the same vector in a different basis. So all that thing that you're sort of puzzled about with representations goes back to this, is sort of like made formal here or explicit. So let's see what the identity representation of the identity map is when B and D are different. Well, let's look at what is the image of V1, the first basis vector. Well, it's the identity map, so the image is V1. But what is the representation of this in basis D? Well, we have to say it's A times V1 plus V2 plus B times V1 minus V2. Now, we know we want to get V1, we want to choose A and B so we get V1, right? But if you look at this, V2 is going to cancel out if I choose A equal to B, right? Because I've got a plus V2 here and a minus V2 here. So if I choose B equals to A here, choose, right? This is going to equal A times V1 plus V2 plus V1 minus V2. The V2s will cancel out, and I'll just be left with 2 times V1. Well, then if I choose A equals to 1/2, this will equal to V1. Okay, so I'm just saying that this is a way of eyeball. I could do Gauss's method somehow with this, but the point is then, so therefore V1 equals 1/2, 1/2 in basis D, right? This is 1/2, this is 1/2. I just motivated why I'm choosing 1/2 I'm choosing A equals B and then choosing them both to be 1/2 means that V1 represented in basis D is 1/2, 1/2. Because what this means is 1/2 of the first one plus 1/2 of the second one The V2s will cancel out. I'll double the V1s, but the 1/2 will cancel out the 2. Right? So I really will get the same vector back. This really is the same vector, just represented differently.
So whatever arbitrary values makes it easier to cancel out.
Excuse me?
So whatever arbitrary values makes it easier to cancel out.
Yes.
Okay.
Yeah, because the point is here, remember, in a basis, the representation of vectors is unique. There's only one solution. So if I could find it by just eyeballing it, that is the solution. Now, if we're given explicit vectors, we would do that by, it's a linear, we have to solve them. There'd be a linear system here we'd have to solve, right? So we could write this into equations and see that I would have to have a plus b equals to 0 and a minus b, or I have to have a plus b equals to 1 and a minus b equals, I could, from this equation up here, I could get a linear system and solve it, and this would be the solution. But I just wanted to sort of, instead of doing it magically like that, I wanted to sort of show you how you could sort of see what was going on inside. But then this gives us the first column of this matrix, right? It's the image of V1. Now let's do the image of, see what's new here is I'm not telling you what V1 and V2 are. But I'm saying I'm just changing, because this other basis here, I'm telling you it's a basis, we'd have to like go through and check that. But okay, what's the image of V2? Well, it's the identity map. So it's V2. And we have to ask, well, that's going to be C times V1 plus V2 plus D times V1 minus V2. Now, if we play the same game, we don't want to have, we want to get rid of V1. That means we want to choose D equals to minus C, right? So if I choose D equals to minus C, I'll have C times V1 plus minus C times V1. The V1s will cancel out, right? And this will equal C times V2. Then the minus sign here will cancel that minus sign. I'll have plus C times V2. So I'll get 2C V2. So I choose C equals to 1/2. So, and that means that D equals minus 1/2, which means that V2 equals 1/2 minus 1/2 in basis D. So if I then see that what the matrix here is, it's going to be 1/2, 1/2, 1/2 minus 1/2 from B to D. So this is the representation of the identity matrix that takes you from vectors in basis B to the same vector in basis D. And you notice that it doesn't matter what basis we choose for B and D. We can choose B and D, the B1 and B2 could be, we could say them anything in the standard basis because we're not choosing a standard basis. So this is a relational thing. It's showing you that if I want to change from this basis to this basis, this is the identity matrix. So the identity matrix doesn't have to be like 1, 0, 0, 1. It doesn't have to, it's not like this is a magical formula. The magic of this 1, 0, 0, 1 is that I'm going from basis to basis. This is different because I'm going from one basis to a different basis. Okay, okay, so let's look then at all the time in the past. We've had say a map F that's gone from V to W. Right? And I've asked you, we've looked and we want to find the matrix F, right? That also takes us in basis B to basis D, right? So in some sense, the map takes us from the vector space vector to the vectors in V to the vectors in W, and F takes us from the vectors in V in basis B to the vectors in W in basis D that gives you the same map here. This is what we've been doing all this time, right? But then the problem has been what I've given you, what you've always had is you've had F in the standard base, V in the standard basis, right? Say E1 to W in the standard basis here. So I've always given you like column vectors to column vectors, right? So I would like your F might be X, Y to X plus Y, X minus Y, right? And then I've asked you, well, what's the representation of this if I choose to? So what I want down here is I want to know what is, I want to know this map where I take this in basis B, right? This is, and this is basis B and basis D. So I've asked you, well, what's the map down here? What's the matrix down here? FBD, where I'm choosing different bases, right? So one way to, this is still the map F, but one way to do this is to find, if let's say I know that what the problem I've given you has been, you know this, you're supposed to find this, right? Well, one way to do this is to find the map that goes from V down here, the identity map, the identity matrix here that takes you from the standard basis to basis B, and the one here that takes you from E2 to D, right? So on the other hand, though, what I really wanted was to start here and go here. So what I actually want is to say, start here, go here. This will be the identity matrix from B to E1. Then I go over here and come down here. So one way to find this matrix was to change bases to here, apply the known thing, and then use the identity, go back this way. So this sort of using identity maps, I could change bases and do all that stuff before that we did before. So I gave you a problem like, here's a map F from XY to X plus Y, X minus Y. And then let's say that we want to, and we can find, let's say, well, I'm giving you this is really in, of course I have to, let me see. Yeah, I have to, okay. Let me just turn that, yeah. Okay. What time is it? It is 11, okay. So we have this map F from XY to X plus Y, X minus Y, and we have it in the standard base. Implicitly, this has been in the standard basis, right? Because this has been X times 1, 0, Y times 0, 1. So we've given this, and I've asked you, well, let's say you have basis B of say, let's say basis B here was say 1, 0, 1, 1, and then basis D was say 1 minus 1 and 0, 1, right? And the question would be, what we can find F from standard basis to standard basis, right? But then the problems would be, what's F from B to D? And so what we've done is you've said, okay, well, we've said, okay, we want to find the basis action for this, so we start from 1, 0, right? Because that's the first basis vector in B. Okay. And implicitly, just by making this choice, you're following, well, I'm taking what is the map from 1, 0 here, from the first basis vector here to the first basis vector here. Well, it's choosing this 1, 0. Okay. Okay, so anyway, so I'm choosing that, then I go to a vector here and say, well, what is the image of this one here? It's going to be 1, 1. Then I'm saying, okay, then I take, well, what's the representation of this vector in this? So I have to sort of go down and find the A and the B here, plus B 0, 1, and then that's going to equal AB in basis D, and then this becomes the first column of matrix BD. This is the problems that you've been doing before, right? So the idea then is that we could find this matrix by going and finding the identity maps, by finding the identity map that would take us from 1, 0 to this map that then goes over here. And that's just what I did here. See, I started from this vector here and then applied this map here to get 1, 1. And then going from this 1, 1, this is essentially in this basis here, and I'm getting it in basis D. It's the same vector. So the map that you're calculating here each time is basically finding the identity, okay? So I'm trying. We could go through and go through all the details, but the point is, all the representation stuff you've been doing has a place of looking at representations of the identity map. So it's not just some kind of ad hoc thing. And so I could represent. Let's see. F BD is going to equal I from B E1, F from E1 to E2, and the identity from E2 to D. So this is so I could find this. I could find the matrix that we've sort of been going through by this maneuver by finding two identity maps and then using the representation of this map here. Okay, so since we only have like 20 minutes left, I could go through this as an example. Maybe we'll do this like next time or something. But the point is that implicitly what I've been giving you is I've been giving you a map in terms of column vectors, say, or some other vectors that are concrete, but they've always been sort of implicitly in the standard basis, and then ask you to find the representation with different bases. I've been asking you to solve this problem here, but we've been doing it by hand. Instead of, we haven't been doing it by finding identity matrices. This method up here that I've told you how to do it sort of does this by hand. And we could go and formalize that so it makes sense. You see what you're doing. Okay. But the problem is we don't have time, I think, to go through and do all the details right now. So, but this is so sort of like, this is what's going on. Let's see, how do you, okay. Yeah, here's one of these, here's the sort of result here that if you want to find H0 from H1, you can follow it directly here, or you can sort of follow it around the other edge of this pathway. This looks complicated, and that's why it's sort of, we don't have to master this. I just wanted to give you, this is sort of, we'll do an example of this in class, but there won't be any homework problems related to this exactly, because we're doing it sort of in this way here, but I wanted you because you've asked questions about, well, what is this thing with why we're changing representations? What we're doing is we're applying an identity map. We're saying, okay, we start with a vector on one basis, we're going to the same vector on a different basis. So it's this idea of the same vector that's behind the identity map, which is mysterious because you can't see, like, how do I know what a vector is? Well, I can't look at it itself. I can only look at it through a given basis, right? I choose a vector xy, but that's always with respect to the standard basis. So I can find the same vector in a different basis, but there's no the vector by itself. You know, like even when I go into the plane and think of vectors as arrows, I can say, well, if I say that it's 25 degrees, you know, north of east, I've still got directions built in. I'm still choosing a basis, even if it's like even if it's like a weird, you know, it's a direction, a length and direct angle basis. Okay, so that's what's behind all this stuff here. Let's see. What can we do that's the last? That's a little bit too far. I want to find one more. I guess I've spent all the time talking and not letting you do anything. Okay, so there's changing representations of vectors and changing map representations. These are the two pieces of things that you've been doing. So a lot of the stuff you've been doing is sort of put on a sound basis in this context. And really that's all we have to do. This is much more concrete. This is much more concrete. This is sort of tying up the loose ends of what we've done with matrices. So maybe the idea is in the last 20 minutes, maybe we should work on a problem together. Let's see if we can find one. In one of these exercises. Okay. Okay, well, let's look at page 447, number 2. Okay, so just number A. Here's a matrix. 1, 2, 3, 4. Nothing special about it. Now, the question is, which of these basic matrices could be used to change bases? Okay. Well, so what does that question mean? To change bases, okay? Matrix to change bases. Well, what that means is it means a representation of an identity map, right? Well, so what we'd have to do is we'd have to say, well, the question is that if we want to have the identity map, right? An identity map is 1-to-1 and onto, right? So if this matrix is going to represent the identity map, it has to be one. If it's going to represent the identity map, it must be 1-to-1 and onto. Okay? Now, if it's 1-to-1 and onto, it has an inverse. And actually, that also corresponds to the fact that it's non-singular. So any non-singular map can be used as a representation of the identity in some basis. You can see that we could disassemble this and say, well, if this is we could choose a basis here and ask we could recover the basis action from this matrix if it is has an inverse. So how would you detect whether it hasn't? If so, to answer this question, what you do is we'd go through and say, well, let's see if it has an inverse, right? Like this. So you'd have to go through and then see if it's. We do -3 row 1 plus row 2 to get 1, 2, 1, 0, and then -3 plus 1 will give me a 0 there, and this would be -6 plus 4 is -2. -3 and 1, and you'd see, well, look, this is already in echelon form, and both variables are leading, so it's going to be non-singular. So we can clearly put it into the right form. So it is non-singular. So all I really had to do was take this matrix, put it into echelon form, and say, oh, well, the two variables are leading. Two leading variables. So this question was sort of a conceptual question. It's misleading in the sense there's nothing magic about a change of basis matrix. A change of basis matrix is a representation of the identity map. And any non-singular matrix can be used as an identity map because it's one-to-one and onto. Okay. Let's how about number 3? It says here 3, find the change of basis matrix for the pair BD where they're both in R2, right? So here is B equals, I'll write this out. This is the standard. This is notation for the standard basis. And the codomain basis equals, here, this is 0, 1, 1, 0. These are the names for the individual vectors in the standard basis. So this is the part A, the cryptic part is to understand the notation. So the question is, what is a change of basis matrix that changes that maps a vector V in basis B in R2 to the same vector in basis D? See if you can find that matrix. Its notation would be identity B to D. And then So you guys are all on the, you guys aren't stuck, right? You know how to get started, or remember the change of basis matrix is you have an identity map and you're asking what's the basis action for the identity map. So you want to look at, say, each of the basis elements in B, find what their image is under the identity map, and then change the basis to basis D, find their representation in basis D. Using just the way that we've done it before. So, Shruti, you have a matrix, okay? Well, we only have 10 minutes left, so maybe I should go ahead and start this. And maybe I'll catch up with. Okay, so if I do this, I'm going to look for the image of 1, 0, which is going to go to 1, 0 because it's the identity map. Okay, implicitly, see, these are given to me in terms of the standard map. So then I have to write this as A times 0, 1 plus B times 1, 0. Well, obviously, I want to choose A to be 0 and B to be 1. So this is going to equal 0, 1 in basis D.
How is that obvious?
Well, this is 1, 0. This is 0, 1, and 1. These are the same vectors. So I can just choose B equals 1, A equals 0. And I do the same thing with the other one. 0, 1 goes to 0, 1, which equals 1 times 0, 1 plus 0 times 1, 0, which equals 1, 0 in basis D. So the answer is 0, 1, 1, 0. And you can sort of see, all I did was change the order of the matrix of the vectors, right? This is just the same vectors, but I switched the order of them. And this is a permutation matrix that swaps X and Y.
The row swap.
Excuse me?
I mean,
Yeah, it's like a
row swap.
yes, exactly. It's a row swap. So so switching basis vectors here, sort of okay, Shruti.
So I don't know if this worked or if it was just I ended up doing something wrong, but I got the right answer. The method that I used was I just multiplied, I turned the basis into a matrix and I turned D into a matrix and I just multiplied D by D. And I got 0, 1, 1, 0. I don't know, was that just a fluke and I ended up getting the right answer or?
The question, so you made a matrix here, and then you made a matrix here.
Yeah, and then I multiplied.
Well, this is the identity matrix, and so the point is that, okay, you can see that this is the image of this vector, right?
Yeah.
And this is the image of this vector.
Mm-hmm.
So this is going to be the matrix you want.
Okay.
Since this is the identity matrix, it doesn't change anything. You multiply them together.
So,
Yeah, I think that if this wasn't,
if it was like not 1, 0, 0, 1.
yeah, I think that it would be, we could try it and see, if there was some magical situation going on, like with one of these other ones here. For example, here, if I formed the matrix 0, 4, 1, 3, and then I multiplied -1, 1, 2, 2 by that, am I going to somehow magically get what the answer is on D. Well, we could always do it in C. Maybe there's some, I mean, there are sometimes those. So why don't you, if you want to do that, then I will look at just doing it the naive way, which is looking at the image of -1, which should be -1, and then having to right? And so here, it's not clear that you don't end up with having to do 0, 4. Then if it did work somehow magically, then the question is why? Because here we're okay. Go ahead. You can do your magical matrix multiplication.
Honestly, I think it's like people have been doing this for linear algebra for a long time, and this has never been the case. And I'm pretty sure I'm wrong. Like,
well, not necessarily, because there are some magical tricks like that, like with things like that work. So what we can do here is, so it looks like I'm going to get is this
no. I'm getting 8587.
okay?
So
Just for rather I just went out to do 0181431.
So are you trying to compare something that I'm moving it back and forth so you can't see it?
So I got, B equals -1, A equals 1,
on the top. You got this one up here, right?
Yeah, so wouldn't the identity matrix left column be one negative one?
Oh, yes. You're right. This one is this one. I quoted the wrong one. 1 minus 1. And this one is going to be minus 1. So you got 1 minus 1. And the second one here, I think this works because we have to have B, it has to be 2. And if that's 6, we need, wait, 6. Yeah, 6 and minus 4 is 2. So we have A is minus 1. Okay. So I think this is the representation of the basis change matrix between these two up here. And we could okay. Well, we're out of time, but we would anyway. So that unfortunately we didn't find a magic method, but it's good to try. You never know. Now, if you look at 4 here, you can see this is all polynomials, right? So this is the same problem as up here, but you're given polynomial vectors. In each case, remember, you're representing vectors by the coefficient. You're given the bases here. So it's probably useful to find the change of basis matrix between two bases between polynomial vectors, because each vector you're representing, you're representing there's going to be a matrix that changes, but this, like the representation here, this is the standard basis for P2. This is a shifted, this is like a permuted basis. So you can see the identity matrix for A is going to be some kind of permutation matrix in 3 by 3 matrix. And similarly, these other ones are going to mix up different stuff, but you should be able to see that what is the representation of a vector in basis B, or basis D, they're going to be column vectors. It goes back and forth with that rule. Okay. Well, I should let you guys continue with this. This is, and we will see you on Thursday.